We've got our last official video, and this one's going to be kind of a quick overview for polymers. Note that I've got it labeled as Chem235. Technically, what we're going to address covers second semester. But polymers, as their own kind of field, deserve their own field. There's a lot of different chemistry that goes into polymer chemistry, and we get a lot of really cool, interesting things happening within it. You get nylon parachutes, plexiglass nucleotides, amino acids. All of those are polymers, and how they are built and maintained and chemically processed so that we get the end result that we want is a fascinating subject that usually requires a lot more than just a one-off lecture, which is what we're getting in OChem because we really don't get the time to really devote to that. So with that, let's try and move through this. Shorthand. So the first thing that you should really kind of pick up within polymers is that these are very, very, very long repeating units. And so we need to come up with some kind of a shorthand to represent them. So let's take a look at the top polymer first and skip over. That's an awesome face. Wish I had actually attempted to make that face. And if we take a look at just that top polymer, we want to be able to describe it. And even as it is, it's a very short section. So envision this extending outwards thousands of times. We don't want to have to go through and draw that molecule every single time. So we want to come up with a shorthand for it. The idea behind the shorthand is to make it as short as humanly possible, but in some circles at least, come up with a way to create a shorthand that makes sense. And we'll see what that sense means in a second. So this particular, we could go through and do a shorthand, and we could put N in this case for the number of times that it repeats. I don't feel like counting it out here, but we could say that that was 10 times, 20 times. Sometimes what you might see in that lower right-hand corner would be 100 to 200 because the people synthesizing it weren't able to nail down a specific number, which is fairly standard, and instead have a general idea on how many times it repeats. To the utility of this, the point or one of the points of a shorthand could also be to address where that polymer came from. So in an amino acid, what you're combining is the varying R groups or the varying amino acids that make it up. So what we would do is try and pick a shorthand that would allow us to see those individual units. If we go through and look at the polymer shown above, though, what would be the starting material? Just a carbon with 2 hydrogens? How does that carbon and 2 hydrogens connect to the next carbon and 2 hydrogens, and to the next 2 carbon and hydrogens, so on and so forth? How did that structure come about? And that becomes a challenge because it would have to be both simultaneously positive and negative and not cause any other kind of weird issues. For those of you screaming carbines, that is a potential, but again, the carbene ends up being a very reactive species that forms in a very limited environment, so it's probably not the best option. So this as a shorthand doesn't give me a lot of information about what built it. Okay? The better shorthand, at least in my opinion, would be to go through and do something like this. Okay? And that shorthand, now shown in blue, we're showing 2 carbons with the CH2s, okay? And one would need to be positive and one would need to be negative. If we then did a repeating structure out, negative, positive, we could envision this polymerizing and creating that connectivity. But how do I get 2 of those carbons next to each other to act as both a positive and a negative? This is where the shorthand becomes powerful because instead of showing the negative and positives outwards, we could bring them inwards, and what we're looking at polymerizing is just an alkene. So the shorthand in blue I would argue is a better shorthand because that allows me to get some concept of what the monomer was, the single starting material was to build this out. Okay? And so that tends to be the most common shorthand usage, is the way of putting parentheses that you could see where the starting material came from. Okay? And in this particular case, with just that straight carbon backbone, alkenes are the easiest place to get these. Okay? So let's test your knowledge and see what you come up with for this one. Okay, so this would be that moment to pause, come up with a shorthand that you think would be appropriate. Okay, so let's assume you've come up with it, and let's say you came up with this as a shorthand. Okay, shown nicely in red. Does that work? Well, if we copied and pasted, copy, paste, do we have all of those same atoms? There's 1, 2, 3 atoms. 1, 2, 3 atoms. 1, 2, 3 atoms. So yeah, this would work. How about the other direction? We'd now be pasting with the left-hand side, or sorry, the right-hand side of it, and yeah, that does work also. Okay, and so that would be a potential place to draw that. How do we get the carbon backbone moving through it? So again, recognizing that our carbon backbone is forming through alkenes, okay, those pi bonds there, we could be looking at a monomer like that. Some people I have seen go through and say, well, hey, couldn't I have just done the single bond there? Well, look at the very next carbon. That very next carbon is a single carbon. If we just did a copy and paste, that's effectively what you do when you're building these polymers out, is copy and paste whatever you've put within the brackets. And you would notice that that doesn't work. But we could expand it out to here. And that would now copy and paste just fine. And that would get us this monomer unit. Well, which monomer unit is correct? Hopefully what you're saying is they're the same thing. We've just flipped our viewpoint of it. This is where IUPAC can step in and say one is valid shorthand and one is invalid. Yes, IUPAC does do that and has created a shorthand notation that some people use, some people don't. Ultimately, what I want you to be able to do is to find that pattern, recognize the backbone. So in this case, the backbone is all carbons. We're doing that from starting from alkenes. Okay? Either of those patterns, red or blue, work. IUPAC says blue because the carbon on the left-hand side in the blue and the carbon on the left-hand side in the red, the blue one is a higher priority because it's more substituted. Okay? Don't shoot the messenger, but that's the rule there. If we go through and look at the polymer on the far left, since now you've got some ideas on how to go through and do this, let's see if you can come up with the repeating unit. Okay. And I'm going to pick right in the middle, do something like this, and say, well, that's where it is. If I copy whatever the symbol is for Control-C, Control-P, and I go right here, the very first atom I should see would be the nitrogen. It's not the nitrogen. If we now go through and look at how we would copy and paste, that next atom should be a nitrogen according to my pasting, which would mean I'm doing it wrong. So my repeating unit isn't valid there. Okay? Instead of just arbitrarily dropping these lines, what I would recommend you do is focus on the weakest bond, because that's the bond that's going to be easiest to make or break. And hopefully what we can see is that that bond between the nitrogen and the oxygen is the most likely bond to break, because that would be our amide bond, the most polar. So that would be a good place to drop a parenthesis. As I continue to move through, I've got carbonyl, carbon, nitrogen, carbonyl, carbon. So I'm starting to see that pattern. If I drop my other parenthesis there, and if I copy and then slide it this way, the first atom I would expect to see would be nitrogen. Yep, carbon, carbonyl. So that works. If I copied and pasted the other direction, I know we have a limited paste window here, but the very first thing I should see would be a carbonyl. And there it is. So that does work as a repeating unit. Okay? That is fine to me, and you would be able to answer any multiple choice by seeing that, okay, by finding that parenthetical. What's happening here, though, is this isn't just a carbon backbone because we're seeing the nitrogen introduced here. We also have that carbonyl carbon causing a polarization. If we go through and split this out, the electrons in that bond are likely to go towards the nitrogen, making this carbon positive. The other bond, the electrons would go again towards the nitrogen, making this one negative. What we're seeing here is an NH2 and then some kind of leaving group. There's an amino acid. Okay, so what you're trying to do is identify those charges and then just replace the missing piece such that you're getting that proper kind of charge maintenance, if you will, as you move through it. Are there other repeating units or places that you could drop parentheticals? Absolutely. Okay, where I started with that nitrogen out front versus here, now it would copy and paste better. Okay, so this is a repeating unit. This would count as a shorthand. And if you ask IUPAC, this is actually a better shorthand than what we just showed. I've got a problem with it though, and that if we look at that structure with a CH2 out here, where did that come from? I'm not generating a reactive carbon here to react with this nitrogen. That's not the bond that's made. The bond that's made is the amide bond. And that amide bond is important because that amide bond was made in a condensation reaction, okay? A nucleophilic addition elimination, which we learned about in Unit 3. That bond becomes so important that we actually named this type of polymer differently than we named the first two that we looked at. This polymer is known as a condensation polymer. The other one's known as an addition polymer. It's so important, the referencing of that bond is so important that we name the polymer differently. And yet the shorthand we use, officially according to IUPAC, doesn't actually draw through that bond. Okay? So be aware that when we're looking at those shorthands, there's all sorts of different patterns that you can find within these. Those patterns aren't necessarily wrong, but there are some that can be more useful than others. When it comes to organic chemistry as a field, okay, organic chemistry, we want the most useful polymer shorthand. So draw it in such a way that you can see the monomer repeating unit. That's the most useful for you. If you moved into polymer chemistry, now you run into kind of gray areas behind what you want. Do you want the most useful or do you want the correct answer? Okay. Everybody's going to fall differently on that spectrum. I just want you to be aware that there is kind of a pseudo debate there. And for those of you saying it's stupid and that it shouldn't be an issue, name H2O. You're probably using the common name, not the IUPAC name. So there are systems where IUPAC becomes more important than others. This just happens to be one of those kind of debates. Bottom one is a new kind of polymer. We might go through and do the same thing that we just did for that top one. Go, okay, Mike, I trust you. The amides, always dangerous to trust me. I'm going to draw it through the amide bonds. So there's my repeating unit. Well, dang it. There's no nitrogens within that repeating unit. Okay. What that means is that that amide bond, which I guess I'll go through and show in red, was not part of the repeating unit. It was made kind of internally. Okay, and that this structure is actually composed of two monomers. I get one that's the diamine, and I get one that's the dicarbonyl. Okay? But to show the whole repeating unit for the entire polymer, I would have to go via purple and show the whole thing, not just an individual monomer. Okay? So recognizing where those bonds can break and make become very useful in identifying what monomers go into it, and they can allow you to build out the larger polymer structure. It takes practice to manipulate these things. Your textbook has a section on polymers. You can read through it. And ultimately, I would recommend you just skip to the end of the chapter and look at some polymer repeats and try and identify that shorthand, because that's really all you need to be able to do when it comes to polymers. Okay. The next part is identifying which one's which. We already kind of touched on it. Straight carbon backbone, addition polymers. If you see carbonyls, really it's not the carbonyl, it's the electronegative atom somewhere in the chain. Those are condensation polymers. So there's two primary polymerizations: condensation and addition. Be able to see those, okay? That's what you're looking for. Your addition polymerizations, because they're alkenes, are typically going through free radical mechanisms. The mechanism isn't super critical. What is kind of critical is, again, recognizing what's causing the polymerization is the alkene, which is going through the backbone. Everything that is attached after the alkene or around the alkene just hangs off of it. Okay? Those would be the kind of side chains, if you will, of the back of our polymer. The condensation polymerization goes through that nucleophilic addition elimination, which we saw in Unit 3. So any of those functional groups that you saw in Unit 3 can be used to make a condensation polymer because they have that potential activity. You just have to add a secondary reactivity to it, like a nucleophile, in this case the amine for our proteins. Free radical polymerizations, you've got your initiation, your propagation, and then what's not being shown here, which would be a termination. So those are the common terms that come from radicals. Initiation, no radical, there is a radical. Propagation, there is a radical, there's still a radical. Termination, there is a radical, no radical. Okay? So recognizing just what's drawn can help you identify those different stages. Being able to identify those is really all you need to be able to do. Okay? Our condensation polymerization, again, look for that carbonyl. That carbonyl is really what's tipping it off. As long as the carbonyl is in the backbone of the polymer, that's looking at a condensation polymerization. Okay? You can also hear reference to anionic and cationic chain growth polymerizations, which is just a fancy way of saying instead of running by a free radical mechanism, you're running by negative charge, anionic, or positive charge, cationic. Okay? So if you look at a particular reaction and say, oh, that would be a nice spot for a negative charge to build, that would be an anionic polymerization potential. Okay? If it was the formation of a positive charge, that would be cationic chain growth. So they're just trying to break down the different categories of how our polymers can form. After that, you're really starting to move into a polymer chemistry class. There's some stuff that's important: crystalline solids versus amorphous solids. So crystalline, those sheets or those polymer chains, and that's what this image is trying to show, stack nicely next to each other. And because they stack nicely, they don't want to move away. So they're very crystalline and rigid. Okay? Amorphous solids, they're all over Helen-Gone. Okay? So they're bendy and flexible. Okay? That means weaker intermolecular forces between the chains. You can reference entropy. Rubber bands are amorphous solids. Crystalline solid polymers, some styrofoams can be crystalline. Some of those tend to be amorphous. A lot of that is how the polymer is actually made, how it's extruded from the system. Okay. And then the last one, which is kind of a random, goofy looking slide because I don't think it's all that important, is our thermal transitions. Because these are by definition impure, because you've got a bunch of different polymer strains, you don't really get kind of a nice melting point. What you'll get is this transition of going from solid to liquid. Okay? And that solid to liquid point, because it's more of a weird gray area, gets referenced as a glass transition temperature, which is really just, it's effectively the melting point, but it can't be a melting point because it's not by definition pure, because they're all different sizes. Okay? And with that, we are done also. And I will again try and reiterate that if you have questions on any content throughout the entire semester or from OChem 1, please ask, send me an email, put posts in Piazza, talk to me about it. Let's make sure that you actually understand everything so that you're ready to go for the final. And with that, we're done. I wish you the best of luck, and hopefully I get to talk to you soon. Have a good day.